Welcome back, Crammers, to question 2. A register stores the binary number. Give the denary number for the binary number stored in the register, and we must show our working. So, moving right to left, we have 2 to the power of 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, and 2 to the power of 7. So, starting from the right, every time there is a 1, we calculate that. So here, 2 to the power of 0 is just 1. Then we have 2 to the power of 1, which is 2. Note how this is 0, so we don't count this, don't count this, don't count this. We have 2 to the power of 5, which is 32. Then we have 2 to the power of 6, which is 64. And 2 to the power of 7, which is 128. If it makes it easier during the exam, just see how each number doubles each time. So we have 1 plus 2 plus 32 plus 64 plus 128. We have 227. So here we just write 227. Give the hexadecimal number for the binary number stored in the register. So we have to break this up into nibbles, and nibbles are 4 digits. So 4 and 4. Starting from the left, we have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. So here we have our first digit is 2 plus 4 plus 8. So that gives us 14. Now, for the second one, we have 2 to the power of 0, 2 to the power of 1, so on and so forth. So we have 2 to the power of 0 is 1, and 2 to the power of 1 is 2, so we get 3. Now, 1 to 9 is just given as 1 to 9. However, 10 to 15 is given as A to F. And note how 14 is greater than 10. So we have 10, 11, 12, 13, 14, 15. 10 is A, so this is B, this is C, D, E, F. So 14 is E, and 3 is just written as 3. So we have E3. A logical shift of 2 places is performed on the binary number stored in the register. Complete the binary register to show its contents after this logical left shift. So when moving logically to the left, that means we remove the left 2 integers and we write 2 zeros on the right. 1, 2. So our value is 1, 0, 0, 0 and 1, 1, 0, 0. The negative denary number negative 99 needs to be stored in the register. Complete the register to show the binary number that would be stored using 2's complement. Show all your working. So when using 2's complement, we simply flip and we add 1. So let's pretend this is just a regular positive 99. So we know that we have, let's just give ourselves 8 digits here. 1, 2, 3, 4. 1, 2, 3, 4. And we know that we cannot subtract 128 from 99. So this will be 0. 99 can be subtracted from 64. Minus 64 gives us 35. So that's 1. We can subtract 32. So that gives us 3. And then we can go farther, farther, farther. We can subtract 2 and then we can subtract 1. Now that we have this binary value for positive 99, we have to flip it. So every 0 is a 1 and every 1 is a 0. And then we just add 1. So our final answer is 1, 0, 1, 1, 1, 0, 0, 1. And we just copy this here. The number 01001100 is added to 111000011. Add the two 8-bit binary numbers using binary addition. Give your answer in binary. Show all your working. So we have 01001100 and we have 11100011. Now we know that 0 plus 0 is 0. 0 plus 1 is just 1. However, 1 plus 1 is 1, 0, and 1 plus 1 plus 1 is just 0. So we can give this as, when we combine, we get 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0 and carry the 1, and we have 1 plus 1 gives us 1, 0. So our final answer is 1001011111. Thanks for watching. Cram, then scram.